All right. Cool. Well, thanks, everybody. So I'm going to give the second talk tonight, which I'm not crazy about, and I don't want this pattern to repeat. But Andrew and I wanted to kick this series off, and felt like me talking twice is better than not. But we're gonna get more diversity of folks. If any of you want to give a talk yourselves or know somebody who you think might, that'd be awesome. But a topic that I feel is important for practitioners to understand is a real sea change in natural language processing that's all of like 12 months old, but is one of these things that I think is incredibly significant in the field, and that is the advance of the transformers. The outline for this talk is to start out with some background on natural language processing and sequence modeling, and then talk about the LSTM, why it's awesome and amazing, but still not good enough, and then go into transformers and talk about how they work and why they're amazing. So for background on natural language processing, NLP, I'm going to be talking just about a subset of NLP, which is the supervised learning part of it. So not structured prediction, not sequence prediction, but where you're taking a document as some input and trying to predict some fairly straightforward output about it, like, is this document spam, right? And so what this means is that you need to somehow take your document and represent it as a fixed size vector, because I'm not aware of any linear algebra that works on vectors of variable dimensionality. And the challenge with this is that documents are of variable length. Right? So you have to come up with some way of taking that document and meaningfully encoding it into a fixed size vector. Right? So the classic way of doing this is the bag of words. Right, where you have one dimension per unique word in your vocabulary. So English has, I don't know, about 100,000 words in the vocabulary, right? And so you have a 100,000 dimensional vector. Most of them are 0 because most words are not present in your document, and the ones that are have some value that's maybe a count or TF-IDF score or something like that. That is your vector. And this naturally leads to sparse data, where, again, it's mostly zeros. You don't store the zeros, because that's computationally inefficient. You store lists of position value tuples, or maybe just a list of positions. And this makes the computation much cheaper. And this works. This works reasonably well. Key limitation is that when you're looking at an actual document, order matters. Right? These two documents mean completely different things. Right? But a bag of words model will score them identically every single time because they have the exact same vectors for what words are present. So the solution to that in this context is n-grams. You can have bigrams, which are every pair of possible words, or trigrams, which are every combination of 3 words, which would easily distinguish between those two. But now you're up to, what is that, a quadrillion dimensional vector. And you can do it, but you start running into all sorts of problems when you walk down that path. In neural network land, the natural way to solve this problem is the RNN, which is the recurrent neural network, not the recursive neural network. I've made that mistake. But RNNs are a new approach to this, which asks the question, how do you calculate a function on a variable length set of input? And they answer it using a for loop in math, where they recursively define the output at any stage as a function of the inputs at the previous stages in the previous output. And then for the purpose of supervised learning, the final output is just the final hidden state here. Right? And so visually this looks like this activation, which takes an input from the raw document X and also itself in the previous time. And you can unroll this and visualize it as a very deep neural network where the final answer, the number you're looking at the end is this, and it's this deep neural network that processes every one of the inputs along the way. Right? And the problem with this classic vanilla RNN, this plain recurrent neural network, is vanishing and exploding gradients. Right? So you take this recursive definition of the hidden state, and you imagine what happens just 3 points in, right? And so you're calling this A function, this A transformation, over and over and over again on your data. Classically in the vanilla case, this is just some matrix multiplication, some learned matrix W times your input X. And so when you go out and say 100 words in, you're taking that W matrix and you're multiplying it 100 times, right? So in simple math, in real number math, we know that if you take any number less than 1 and raise it to a very high dimensional value, very high exponent, you get some incredibly small number. And if your number is slightly larger than 1, then it blows up to something big. And if your exponent's even higher, if you have longer documents, this gets even worse. And in linear algebra, this is about the same, except you need to think about the eigenvalues of the matrix. So the eigenvalues say how much the matrix is going to grow or shrink vectors when the transformation is applied. And if your eigenvalues are less than 1 in this transformation, you're going to get these gradients that go to 0 as you use this matrix over and over again. If they're greater than 1, then your gradients are going to explode. Right? And so this made vanilla RNNs extremely difficult to work with and basically just didn't work on anything but fairly short sequences. Right? So LSTM to the rescue. Right? So I wrote this document a few years ago called The Rise and Fall of LSTM. So LSTM came around in the dark ages, and then it went into the AI winter. It came back again for a while, but I think it's on its way out again now with transformers. So LSTM, to be clear, is a kind of recurrent neural network. It just has this more sophisticated cell inside. And it was invented originally in the dark ages on this stone tablet that has been recovered into a PDF that you can access on Sepp Hochreiter's server. I kid, but Sepp and Jürgen are both great. I enjoy them both quite a bit. But they did a bunch of amazing work in the 90s that was really well ahead of its time and often get neglected and forgotten as time goes on. That's totally not fair because they did amazing research. So the LSTM cell looks like this. It actually has 2 hidden states, and the input coming along the bottom, and the output up the top again, and these 2 hidden states. And I'm not going to go into it in detail, and you should totally look at Christopher Ola's blog post if you want to dive into it. But the key point is that these transformations, these are the matrix multiplies, right? And they are not applied recursively on the main hidden vector. All you're doing is you're adding in, or the forget gate, you actually don't really need it, but you're adding in some new number. And so the LSTM is actually a lot like a ResNet. It's a lot like a CNN ResNet in that you're adding new values onto the activation as you go through the layers. Right? And so this solves the exploding and vanishing gradients problems. However, LSTM is still pretty difficult to train because you still have these very long gradient paths. Even with those residual connections, you're still propagating gradients from the end all the way through this transformation cell over to the beginning. And for a long document, this means very, very deep networks that are just notoriously difficult to train. And more importantly, transfer learning never really worked on these LSTM models. Right? One of the great things about ImageNet and CNNs is that you can train a convolutional net on millions of images in ImageNet and take that neural network and fine-tune it for some new problem that you have. And the starting state of the ImageNet CNN gives you a great place to start from when you're looking for a new neural network, and makes training on your own problem much easier with much less data. That never really worked with LSTM. Sometimes it did, but it just wasn't very reliable. Which means that anytime you're using an LSTM, you need a new labeled data set that's specific to your task. And that's expensive. Okay, so this changed dramatically just about a year ago when the BERT model was released. So you'll hear people talk about transformers and Muppets together. And the reason for this is that the original paper on this technique that describes the network architecture was called the transformer network. And then the BERT paper is a Muppet, and there's an Elmo paper, and researchers just run with the joke. So this is just context so you understand what people are talking about if they say, we'll use a Muppet network. Right, what the heck are you talking about, a Muppet network? So this, I think of as the natural progression of this sequence of document models. And it was, the transformer model was first described about 2.5 years ago in this paper, Attention is All You Need. And this paper was addressing machine translation. So think about taking a document in English and converting it into French, right? And so the classic way to do this in neural network is encoder-decoder. Here's the full structure. There's a lot going on here, right? So we're just going to focus on the encoder part because that's all you need for these supervised learning problems, and the decoder is similar anyway. So zooming in on the encoder part of it, there's still quite a bit going on, and so but basically there's three parts. We're going to talk about, first we're going to talk about this attention part, then we'll talk about the part at the bottom with the positional encoding. The top part's just not that hard, it's just a simple, fully connected layer. So the attention mechanism in the middle is the key to making this thing work on documents of variable length. And the way they do that is by having an all-to-all comparison. For every layer of the neural network, it considers for every output of the next layer, it considers every possible input from the previous layer in this n-squared way. And it does this weighted sum of the previous ones where the weighting is the learned function, right? And then it applies just a fully connected layer after it. But this is great for a number of reasons. One is that you can look at this thing and you can visually see what it's doing. So here is this translation problem of converting from the English sentence, the agreement on the European Economic Area was signed in August 1992. And to translate that into French, my apologies, l'accord sur la zone économique européenne a été signé en août, I forgot, 1992. Right, and you can see the attention, so as it's generating the each token in the output, it's starting with this whole thing as the input, and it's generating these output tokens one at a time, and it says, okay, first I got to translate the. The way I do that, it translates into la, and all I'm doing is looking at this. Next I output accord, all I'm doing is looking at agreement. Then sur is on, la is the. Okay, now, interesting, European Economic Area translates into zone économique européenne. So the order is reversed, right? And you can see the attention mechanism is reversed also, right? So you can see very clearly what this thing is doing as it's running along. And the way it works in the in the transformer model, the way they describe it is with query and key vectors. So for every output position, you generate a query, and for every input that you're considering, you generate a key, and then the relevance score is just the dot product of those two. Right, and to visualize that, you first you combine the query and the key values, and that gives you the relevance scores. You use a softmax to normalize them, and then you do a weighted average of the values, the third version of each token, to get your output. Now, to explain this in a little bit more detail, I'm going to go through it in pseudocode. So this looks like Python. It wouldn't actually run, but I think it's close enough to help people understand what's going on. So you've got this attention function, right? And it takes as input a list of tensors. I know you don't need to do that. A list of tensors, one per token on the input. And then the first thing it does, it goes through everything in the sequence, and it computes the query, the key, and the value by multiplying the appropriate input vector by Q, K, and V, which are these learned matrices, right? So it learns this transformation from the previous layer to whatever should be the query, the key, and the value at the next layer. Then it goes through this double nested loop, right? So for every output token, it figures out, okay, this is the query I'm working with, and then it goes through everything in the input, and it multiplies that query with the key from the possible key, and it computes a whole bunch of relevance scores, and then it normalizes these relevance scores using a softmax, which makes sure that they just all add up to 1. So you can sensibly use that to compute a weighted sum of all of the values. So now you just go through, for each output, you go through each of the input tokens, the value score, which was calculated for them, and you multiply it by the relevance. This is just a floating point number from 0 to 1, and you get a weighted average, which is the output, and you return that. So this is what's going on in the attention mechanism, which can be pretty confusing when you just look at a diagram like that. But I hope this explains it a little bit. I'm sure I'll get some questions on this. So relevance scores are interpretable, as I say, and this is super helpful, right? Now an innovation, I think it was novel in the transformer paper, is multi-headed attention. And this is one of these really clever and important innovations that it's not actually all that complicated at all. You just do that same thing, that same attention mechanism 8 times, whatever value of 8 you want to use. And that lets the network learn 8 different things to pay attention to. So in the translation case, it can learn an attention mechanism for grammar, one for vocabulary, one for gender, one for tense, whatever it is, right? Whatever the thing needs to, it can look at different parts of the input document for different purposes and do this at each layer, right? So you can kind of intuitively see how this would be a really flexible mechanism for processing a document or any sequence. Okay, so that is one of the key things that enables the transformer model. That's the multi-headed attention part of it. Now let's look down here at the positional encoding, which is critical and novel and critical innovation that I think is incredibly clever. So without this positional encoding, attention mechanisms are just bags of words, right? There's nothing saying what the difference is between work to live or live to work, right? They're just all positions. They're all equivalent positions, and you're just going to compute some score for each of them. So what they did is they took a lesson from Fourier theory and added in a bunch of sines and cosines as extra dimensions. Sorry, not as extra dimensions, but onto the word embeddings. So going back. So what they do is they take the inputs, they use word to vec to calculate some vector for each input token, and then onto that embedding, they add a bunch of sine and cosines of different frequencies, starting at just pi and then stretching out longer and longer and longer. And if you look at the whole thing, it looks like this. And what this does is it lets the model reason about the relative position of any tokens, right? So if you can kind of imagine that the model can say if the orange dimension is slightly higher than the blue dimension on one word versus another, then you can see how it knows that that token is to the left or right of the other. And because it has this at all these different wavelengths, it can look across the entire document at kind of arbitrary scales to see whether one idea is before or after another. The key thing is that this is how the system understands position and isn't just a bag of words when doing the attention. Okay, so transformers, those are the 2 key innovations, is positional encoding and multi-headed attention. Transformers are awesome, even though they're n squared in the length of the document. These all-to-all comparisons can be done almost for free in a modern GPU. GPUs change all sorts of things, right? You can do a 1,000 by 1,000 matrix multiply as fast as you can do a 10 by 10 in a lot of cases, because they have so much parallelism, they have so much bandwidth, but a fixed latency for every operation. So you can do these massive, massive multiplies almost for free in a lot of cases. So doing things in n squared is not actually necessarily much more expensive, whereas in an RNN, like an LSTM, you can't do anything with token 11 until you're completely done processing token 10. Right? So this is a key advantage of transformers. They're much more computationally efficient. Also, you don't need to use any of these sigmoid or tanh activation functions which are built into the LSTM model, these things that scale your activations to 0 or 1. Why are these things problematic? So these were bread and butter in the old days of neural networks. People would use these between layers all the time. They make sense. They're kind of biologically inspired. You take any activation, you scale it from 0 to 1 or -1 to 1. But they're actually really, really problematic because if you get a neuron which has a very high activation value, then you've got this number up here, which is 1, and you take the derivative of that, and it's 0, or it's some very, very small number. And so your gradient descent can't tell the difference between an activation up here and one way over on the other side. So it's very easy for the trainer to get confused if your activations don't stay near this middle part, right? And that's problematic. Compare that to ReLU, which is the standard these days. And ReLU, yes, it does have this very, very large dead space, but if you're not in the dead space, then there's nothing stopping it from getting bigger and bigger and scaling off to infinity. And one of the reasons why, one of the intuitions behind why this works better, as Jeffrey Hinton puts it, is that this allows each neuron to express a stronger opinion. right? In in a sigmoid, there is really no difference between the activation being 3 or 8 or 20 or 100. The output is the same, right? All it can say is kind of yes, no, maybe, right? But with a ReLU, it can say an activation of 5 or 100 or 1,000, and these are all meaningfully different values that can be used for different purposes down the line, right? So each neuron can express more information. Also, the gradient doesn't saturate. We talked about that. Very critically, and I think this is really underappreciated, ReLUs are really insensitive to random initialization. If you're working with a bunch of sigmoid layers, you need to pick those random values at the beginning of your training to make sure that your activation values are in that middle part where you're going to get reasonable gradients. And people used to worry a lot about what initialization to use for your neural network. You don't hear people worrying about that much at all anymore. And ReLUs are really the key reason why that is. Also, ReLU runs great on low precision hardware. Those smooth activation functions, they need 32-bit float. Maybe you can get it to work in 16-bit float sometimes, but you're not going to be running it on 8-bit int without a ton of careful work, and that is the kind of thing that's really easy to do with a ReLU-based network. And a lot of hardware is going in that direction because it takes vastly fewer transistors and a lot less power to do 8-bit integer math versus 32-bit float. It's also stupidly easy to compute the gradient. It's 1 or it's 0, right? You just take that top bit and you're done. So the derivative's ridiculously easy. ReLU has some downsides. It does have those dead neurons on the left side. You can fix that with a leaky ReLU. There's this discontinuity in the gradient of the origin. You can fix that with GALU, which Bert uses. And so this brings me to a little aside about general deep learning wisdom. If you're designing a new network for whatever reason, don't bother messing with different kinds of activations. Don't bother trying sigmoid or tanh. They're probably not going to work out very well. But different optimizers do matter. Atom is a great place to start. It's super fast. It tends to give pretty good results. It has a bit of a tendency to overfit. If you really are trying to squeeze the juice out of your system and you want the best results, SGD is likely to get you a better result, but it's going to take quite a bit more time to converge. Sometimes RMS prop beats the pants off both of them. It's worth playing around with these things. I told you about why I think SWA is great. There's this system called Attitune that my old team at Amazon released where you don't even need to pick a learning rate. It dynamically calculates the ideal learning rate schedule at every point during training for you. It's kind of magical. So it's worth playing around with different optimizers, but don't mess with the activation functions. Okay. Let's pop out, right? There's a bunch of theory, a bunch of math and ideas in there. How do we actually apply this stuff in code? So if you want to use a transformer, I strongly recommend hopping over to the fine folks at Hugging Face and using their transformer package. They have both PyTorch and TensorFlow implementations, pre-trained models, ready to fine-tune, and I'll show you how easy it is. Here's how to fine-tune a BERT model in just 12 lines of code. You just pick what kind of BERT you want. The base model that's paying attention to upper and lower case. You get the tokenizer to convert your string into tokens. You download the pre-trained model in one line of code. Pick your data set for your own problem. Process the data set with the tokenizer to get train and validation splits. Shuffle them, batch them. 4 more lines of code. Another 4 lines of code to instantiate your optimizer. Define your loss function. Pick a metric. It's TensorFlow, so you got to compile it, and then you call fit, and that's it. That's all you need to do to fine-tune a state-of-the-art language model on your specific problem. And the fact that you can do this on some pre-trained model that's seen tons and tons of data that easily is really amazing. And there's even bigger models out there, right? So NVIDIA made this model called Megatron with 8 billion parameters. They ran hundreds of GPUs for over a week, spent vast quantities of cache. Well, I mean, they own the stuff, but so not really. But they put a ton of energy into training this. And I've heard a lot of people complaining about how much greenhouse gas comes from training a model like Megatron. And I think that's totally the wrong way of looking at this because they only need to do this once in the history of the world, and everybody in this room can do it without having to burn those GPUs again. Right? These things are reusable and fine-tunable. I don't think they've actually released this yet, but but they might and somebody else will, right? So you don't need to do that expensive work over and over again, right? This thing learns a base model really well. The folks at Facebook trained this Roberta model on 2.5 terabytes of data across over 100 languages. And this thing understands low resource languages like Swahili and Urdu in ways that it's just vastly better than what's been done before. And again, these are reusable. If you need a model that understands all the world's languages, this is accessible to you by leveraging other people's work. And before BERT and Transformers and the Muppets, this just was not possible. Now you can leverage other people's work in this way, and I think that's really amazing. So to sum up, the key advantages of these transformer networks, yes, they're easier to train, they're more efficient, all that yada, yada, yada. But more importantly, transfer learning actually works with them, right? You can take a pre-trained model, fine-tune it for your task without a specific data set. And another really critical point, which I didn't get a chance to go into, is that these things are originally trained on large quantities of unsupervised text. You can just take all of the world's text data and use this as training data. The way it works very, very quickly is kind of comparable to how Word2Vec works, where the language model tries to predict some missing words from a document. And that's enough for it to understand how to build a supervised model using vast quantities of text without any effort to label them. LSTM still has its place. In particular, if the sequence length is very long or infinite, you can't do n squared, right? And that happens if you're doing real-time control, like for a robot or a thermostat or something like that. You can't have the entire sequence. And if for some reason you can't pre-train on some large corpus, LSTM seems to outperform transformers when your dataset size is relatively small and fixed. With that, I will take questions while you look at these references. Yes. Yeah, Word CNN. How do you compare Word CNN to Transformer? So when I wrote this paper, the rise and fall of LSTM, I predicted that time that Word CNNs were going to be the thing that replaced LSTM. I did not see this this transformer thing coming. So a Word CNN has a lot of the advantages in terms of parallelism and the ability to use ReLU. And the key difference is that it only looks at a fixed size window, fixed size part of the document, instead of looking at the entire document at once. So it's got a fair amount fundamentally in common. Word CNNs have an easier time identifying bigrams, trigrams, things like that, because it's got those direct comparisons, right? It doesn't need this positional encoding trick to try to infer with Fourier waves where things are relative to each other. So it's got that advantage for understanding closely related tokens, but it can't see across the entire document at once, right? It's got a much harder time reasoning, like a Word CNN can't easily answer a question like, does this concept exist anywhere in this document? Whereas a transformer can very easily answer that just by having some attention query that finds that regardless of where it is. Right? A CNN would need a very large window or a series of windows cascading up to be able to accomplish that. But